I just want to give you a little tour on how you can perform your own tracing and your own spectral extraction if you want it directly from the pipeline product. This is important because, again, you can join it with your own scripts. So one of the things that the pipeline does not do right now is doing spectral tracing. And spectral tracing, for those of you folks that are new to spectroscopy in general, spectral tracing is the art of figuring out where the spectrum is. So of course you can see by eye that the spectrum goes here. So this is order 1 and this is order 2. And the art of tracing is figuring out exactly where this lies. And this is important for many reasons. One reason is that you want to know if the spectrum moves a little bit to extract the spectrum at the correct positions, but also it's important to keep track of the traces as a function of time. So JWST will have like an exquisite precision in terms of guiding, of keeping the spectrum at the same place at each integration, but still there might be some jitter to it. So you want to track that jitter, and one way of doing that is doing it through spectral tracing, to figure out the traces at each of the integrations and using that time series maybe to decorrelate your data at the end of when you do the light curve analysis, for instance, etc. I really encourage you folks to go and check out some papers by Everett Laughlin from this year. So for example, here you have in the x-axis like kind of the expected shift for NIRCam in particular, the expected shift in pixel space of the JWST centroiding basically, and in the y-axis is basically what kind of flux that imprints on your light curves. So it's in the order of like 100 parts per million basically, which sounds small, but this is the kind of stuff that we really want to do, for instance, for tracing in exoplanet science. So keeping track of pixel movements at the order of like a tenth of a pixel is really, really important. And tracing can really help with that. And I'm gonna go into detail now to what this function does, but this is a very simple function that just traces the spectrum of nearest source data. And I'm just gonna show you how well it does. Just gonna go quickly through it. So, this is just the centroiding at each integration, plotted on top of each other, and it does pretty nicely. So I'm gonna do the same for order 1 and order 2. So once I have the traces, just gonna go again quickly through this. Once I have those traces, and just plot them, and these are the traces for each integration, and they look very, very nice. Nice thing is that you can track the movement with this simple algorithm for tracing, for instance. You can track the movement of of the actual trace down to 100th of a pixel, and this is enough for tracking purposes of the movement of the trace. In the next section, what I do here is that you remember that I told you that I just took the median at each column to remove 1/f noise, and that was giving some kind of weird effects. So now what I do is that using these traces, now I know where the spectrum is located. I just mask all the illuminated pixels, and I do this median column by column again, but not including those illuminated pixels. And when you do that, this 1/f correction looks much better. This is in the bottom. So especially here, where I had these dark regions, now they're no more. So I feel happy with that. Next step that I do here, it's spectral extraction. Again, one of the details, so the JWST pipeline can get you a spectral extraction, but it cannot do spectral extraction following any traces because the pipeline does not trace the spectrum. So what I'm doing here is that I'm using the traces that I extracted and just extracting the spectrum. So I'm just basically, this is just a sum, and I'm visualizing here. I'm just summing up all the pixels in these regions here, in red for order 1 and in blue for order 2. And I'm because I have where the spectrum is located, and with the wavelength map that I had before, I know at which wavelengths each of those portions pertain to. I can just extract that and plot that for every integration. So this is what I'm doing here. I'm just gonna be performing this spectral extraction, extracting the fluxes and the errors. And then I just, using the wavelength map that I showed you that you can extract from the JWST pipeline, I'm just extracting the wavelengths at each of those columns. So to what wavelength does that column represent? And with that, I can just extract the spectrum and plot it and see how I do. So I'm doing pretty well in general, except for a handful of bad pixels that I'm not flagging and I'm not correcting for. So this is very like a rough kind of extraction. And if you do a close-up, one of the beautiful things that you will be able to do with JWST data, if you get this kind of precision that I'm showing in these simulations, you can actually see, so you remember that this data set was like a bunch of integrations were in transit and a bunch of integrations were out of transit. Well, you're seeing in and out of transit, so I'm plotting all the spectra at each integration, one on top of each other. So the ones that locked up at the top are out of transit spectra, and the ones that are in the bottom are in transit spectrum. So you can see the transit in the spectrum, which is kind of mind-blowing. JWST precision for you. That's it. Of course, what we can do next is plot the light curves. So this same thing, we can plot it as a function of light curve. So what we do is that I just, for each wavelength here, I just add up the flux and I put that flux as a function of time. So that's what I'm doing here. So there's several ways of visualizing light curves. So one obvious way is just plotting the light curves of each wavelength, one on top of each other, like what I'm doing here. And of course, we can see the transit, which is nice, but I cannot see what's happening at each wavelength. So one of the things that I recommend doing is instead doing this image of the light curves. So what I'm showing as colors is the flux, and the x-axis is the wavelengths, and the y-axis is the integrations. So the very first integration starts on the top, the very last integration is going to the bottom, and wavelengths goes from red to the left to blue to the right, which follows the shape of the actual source frame that I showed you before. And you can see the transit here as well. So lighter regions are in transit, they have lower fluxes, darker regions out of transit. So this is beautiful because it allows you to directly see if there's something wrong at certain wavelengths or at certain integrations. So the same outliers that I was seeing in the spectrum here, they are obvious as well on this image, here. So you can track this back to the integrations and the wavelengths. So that's a very nice thing to do. In this final minute, I just want to explain a little bit of what you can explore in these light curves. One of the plots that I recommend you do is a sensitivity analysis, I call it, which is basically plotting the scatter of your data, of your residuals if you feed a transit, over the estimated error bars by the pipeline or by any mean that you do on your own. And this should line up around 1 if you really understand your error bars. So in this case, this does not line up around 1. It's like 1.5. It's like 50% above the expected error bars. So that either means that my scatter in the data is larger than expected, or that my estimated error bars are too small. So I have a series of exercises for the reader on how to improve this. With the reduction, I'm going to leave it to you, but that's a very good analysis to do. And the other very obvious thing to do is to make the white light curve that we call. So we extract all the flux from all the wavelengths. We plot the light curve of that. That gives you a very high signal to noise ratio light curve, and explore the systematics out of transit. You can do that in whichever mean you want. What I'm doing here is plotting the power spectral density of the out of transit data. There's nothing, so there's no correlated noise actually added to this data. Or you can also do this Allen variance plots, in which you bin your data at different bin sizes, and you plot the scatter of your time series as a function of those bin sizes. So if it is white noise, so if you don't have correlated noise, this should follow this 1 over square root of n. But if not, then you should see some variations around it. And again, here it just shows like the expected behavior of 1 over the square root of n. Before calling the end of this thing, of this notebook, I wanted to point out 2 things. First, TSO timestamps. The precisions we're going to be exploring it during commissioning, but one of the very important things that I wanted to mention is that timestamps are different depending where you are in the detector. So the pipeline currently doesn't tell you this, but this is due to the fact that the pixels are read sequentially. So the very left pixels in this case are read first, and the very right hand ones are read last. So that means that the left one sees any event that is happening before the ones that are in the red. So there's going to be some offset. Now we're working on either giving you those corrections or for you to do it on your own, but they should be typically small. They're 0.5 seconds, but still have that in mind. And just as a mean of summary, TSOs are rich of details. Start exploring them as soon as possible. First point, be critical of the pipeline, which is in constant development. So please reach out if you find anything. Be sure to double check every step of each stage. don't use the pipeline blindly again. Never. Not this one, not any pipeline. And 3, remember that what you saw today is not the final word on how to analyze real JWST data. So this will evolve with time, especially after commissioning, and especially after cycle 1. This is going to change.